Welcome to tonight's public lecture. My name is Matthew Bales. I'm a professor here in the Centre for Astrophysics and Supercomputing, and Pablo Rosado is our guest speaker today. Pablo did his PhD at the Albert Einstein Institute, and he's been working on the search for gravitational waves and studies of gravitation with our group here at Swinburne. And I'm very excited to introduce Pablo, and would you welcome him to the stage to give our talk.
Welcome, everyone. Hi, welcome. I'm going to talk about gravitational waves. I'm really proud to be here giving the first public lecture of the year in astronomy about one of the biggest discoveries in the history of science. Because recently, the 14th of February, it's a very special day, right? Everybody knows why. Exactly. It was the 5-month anniversary of the first detection of gravitational waves. It happened in September 14, 2015. So yes, I'm going to talk as well about a love story of Alice and Bob. They're a pair of black holes, and their love story is unique. So that's what this talk is about. And let's get started. So can everybody hear me? Well, can everybody see me? Sounds like a silly question, but if you can see me, it's because there is some light coming from the sun. It has been traveling for about 8 minutes across the whole solar system. It has gone across the atmosphere of the Earth. It's going through those windows. It's bouncing on me, and it's going back to your eyes. And that's why you can see me. But if we could close the windows and make everything dark here, then what would happen? If we could close all the windows, what would happen is that you probably would do this and try to see around what's happening. But if you didn't have a cell phone, then you would not be able to see me. But still, I will be emitting light. I am emitting light, and so are you, and every object that are around you. You are all emitting light. This is what we usually see. This is the visible light. But we're also emitting infrared light. It's just, we cannot see it, but it's also emitted. We are emitting that. Our eyes cannot see that. But if you were, for example, a predator, who has seen that movie? Who remembers that? Please? Yeah, everybody knows it. Okay. Predator. They were extremely accurate human hunters because they could see us in the dark, because we emit infrared light and they can see that. So yeah, that's, by the way, another very nice love story. So I will talk later about objects that do not emit any light, and they do not reflect any light. They are black holes. But before I get into that, I will keep on talking a little bit about what light actually is. And light is a wave. And yes, what is a wave? A wave is just a perturbation that moves in space and time. So you have, for example, a lake, you throw a stone there, and you will see some ripples moving across the surface of the lake. And light is an electromagnetic wave. Why? Because it's a perturbation of the electromagnetic field. That sounds maybe a bit too scientific, but it's not. Everybody knows what electricity is and what magnetism is. So electromagnetism is the combination of the two. So a light can be described by a certain amplitude. And if you increase the amplitude of the wave, the light will be brighter. And if the amplitude decreases, the light will be dimmer. It will be fainter. On the other hand, the frequency of the light is related to the color of the light. If you decrease the frequency of the light, it will look more like reddish, and if you increase the frequency, it will look rather blue. So we can see only this part of the entire range of frequencies that light actually is. So this is the visible frequencies. This is all that our eyes can see. But the entire electromagnetic spectrum, all the possible frequencies that light can have, is much bigger than that. We can only see a small fraction of frequencies. That's the visible part of the spectrum. But we have also infrared, microwave, radio telescopes. On the other side of the spectrum, we have also ultraviolet, X-rays, gamma rays. We have a lot of different observatories working at different frequencies to cover the entire electromagnetic spectrum. So predators, for example, look, they can see stuff here, right, at the infrared. This is what we can see. And now I'm asking you, where are gravitational waves in this plot? Wow, good answer. Nowhere. They're nowhere here. They're neither here or there or low frequencies, high frequencies. They're simply not electromagnetic waves. They're another thing. They're a totally different spectrum. And that spectrum has opened now with the first observations. So there is a totally new window to the universe that just opened in September 14, 2015. Okay. The rest of the talk will be to address these questions. Who are Alice and Bob? How were they born? How did they get together? Where is their story written? And how can we learn their story? So in other words, in more scientific words, the rest of the talk is going to be about first defining what black holes are, then how do black holes form, how do black holes form binaries, and how do they merge. I will explain what gravitational waves are and how can we detect them. So first of all, what are black holes? There are maybe two possible definitions of a black hole. One is a mathematical one, and the other one is an astrophysical one. First, I will start with a mathematical definition, and I will not use any math to do that. So first, I have this car. I'm going to throw it up in the air, and I'm going to catch it, and nobody's surprised, right? I just throw it up. The gravitational pull of the Earth is bringing it back down, and I catch it, surprisingly. I trained before at home. So if I throw this car up in the air very, very fast, like at 40,000 kilometers per hour or so, what will happen? Let's assume that there's no air, there's no friction, fine. Okay. If I throw this car at 40,000 kilometers per hour, it will go up in the air very high at some point. Even if the gravitational pull of the Earth is pulling it very strongly, at some point it's so far up there that it doesn't feel it that much, and at some point it just escapes. So that's the escape velocity. At some point, if I throw it really, really fast up in the air, the car will escape from the gravitational pull of the Earth. Fine. Now, let's do another experiment. Imagine that you have a pipeline and you're taking mass out of Mars and you're putting it inside Earth, and you're keeping the radius of Earth fixed, okay? So the Earth has always the same size, but you're making it more massive. So as the mass of the Earth increases, I will feel heavier and heavier. So if I want to throw this car up in the air, I have to throw it slower or faster? What do you think? Faster. I have to throw it much faster in order for it to escape. At some point, if we increase the mass of the Earth enough, I will have to throw this car up in the air at 300,000 kilometers per second. And what is that? That is the speed of light. So at some point, if the Earth is so massive that I have to throw this car up in the air faster than that, the Earth will be a black hole. So that's why black holes are black, because nothing that is trying to escape from a black hole can do it. Not even light, because light cannot travel faster than light. So that is the mathematical definition of a black hole. But, as I said, I'm going to give another definition of a black hole, and it's the astrophysical one. So depending on the mass of the black hole, we can have different types of black holes. For example, if the mass of the black hole is similar to the mass of the sun, we call them stellar mass black holes. If they are really, really massive, like millions or billions times the mass of the sun, then we call them supermassive black holes. And if they have intermediate mass, we call them intermediate mass black holes. Okay? So they are black. We cannot see them. They don't emit any light. But if there is stuff around them, like, some gas or some dust or something around the black hole, those particles are going to fall into the black hole, or they're going to be accelerated. And charged particles, when they move and they're accelerated, they emit light. So that's why we can see black holes indirectly. And of course, there is another way to see black holes, and that's the one that brought all of you here. I will talk about that a bit later. So, how do black holes form? Again, depending on the type of black hole that we are talking about, I could explain one possible mechanism or another, but I'm going to just say the typical one, the most typical one. That mechanism is a supernova. So the fact is that stars are usually in equilibrium because they have a lot of fuel inside. They're having a lot of explosions, nuclear reactions inside. That's why actually they're bright, right? But if they lose all the fuel, if they lose all the hydrogen and helium that they are burning, then they're not canceling out the pull of gravity, so they collapse. And when they do that, a supernova happens, and that's one of the most luminous phenomena in the universe. That's where all the material that is produced inside a star is spread around. In fact, all the elements in our body, they have been processed inside a star. If the stars were selfish and they just were keeping those elements for themselves, then we would never be here. The fact that they explode and they spread all these elements around, that's why we can form planets and other stars, and that's why at some point we have our bodies and like we can do presentations and stuff like that. So we have to thank supernovas for that. And in fact, something that probably you should take as a takeaway message, and is that next time that you step in dog poo, I have good news and bad news. Okay, the bad news is that that stuff came out of the butt of an animal, which is not nice, but the good news is that it's stardust. Okay, that really changed my life. I see things from a different perspective now. So what is left behind after a supernova is that compact object. It's a very, very dense and rather small object, like, for example, a neutron star or a black hole. Okay, we know now how black holes form. Now let's talk about how black hole binaries form. What is a binary, by the way? The Earth and the Moon, for example, that's a binary system. It's just two objects that are orbiting around each other. So if you have two massive stars and they both go supernova, if they survive, there you go. You have a simplest way to produce a black hole binary. But those are stellar mass black hole binaries. And I will explain to you now how supermassive black hole binaries form, just because it's really cool. So we have seen that in our own galaxy, at the center, some stars are moving around something that is black. It's invisible, but they're moving around something that should be very heavy. And it should be like about 1 million times the mass of the sun. And that's not only it. We have seen that same sort of behavior in other galaxies around, and we have inferred that most galaxies actually host a supermassive black hole in their centers. Galaxies merge. We have seen that many times. We look up in the sky and we see galaxies in the process of merging towards each other. So if two galaxies that have a black hole inside, if they merge, at some point the two black holes are going to get closer and closer to each other and eventually form a binary. So recently I was in the middle of the night. I just woke up. I was very inspired, maybe because of Valentine's Day or something, and I wrote a poem about Alice and Bob, and I'm going to read it to you. Alice and Bob were both born in a catastrophic event where their progenitors died. They were left alone in the dark. No one could see them. No one could hear them. They were just lost in space. However, they were meant to be together. It took Alice and Bob a long time to get closer to each other. At some point, they start a ritual mating dance, drawing a perfect inward spiral, distorting space and time, and revealing the deepest secrets of gravity. All of a sudden, they can't stand being separated anymore. Their attraction is so strong that they deform, they twist, and simply melt into one another. Space-time is screaming in its loudest voice as they start to embrace. they finally merge into one to share the same horizon forever, inseparable, with such passion that the universe will never forget it. Sorry, it's not very romantic, but that's the best I can do it. It sounded like maybe science fiction, some weird romantic science fiction from a nerd like me, but it's actually, all what I said is based on true facts. So that's actually how a black hole binary merger looks like. I mean, this is an animation, obviously, but what we see is that two black holes get closer and closer to each other. And when they do that, they are distorting space-time, and they're emitting gravitational waves, which are these ripples that you see here in this animation. And at some point, they're so close to each other that the two black holes start to deform, merge, and they become one. And black holes grow by eating other black holes and eating other stuff. So they're eating stuff all the time. Supermassive black hole binaries, for example, they grow by when galaxies eat each other. It's cannibalism, like redback spiders. Redback spiders, when they mate, the female eats the male while doing it. Isn't that romantic? So that's what black holes do as well. Okay, we now know how black holes form. We know what they are. We know how black hole binaries form. And now the message that we hear from black hole binaries, that message is in form of gravitational waves. And I'm going to explain that by doing some general relativity experiments. Imagine that I can travel 3 meters in 3 seconds, okay? So I will try. I was training again at home, so I think I can do it. So I will do it. I will do 1, 2, 3. I just did it. 3 meters in 3 seconds. Thank you very much. Thank you. I don't know if I can repeat it. Please don't ask me to. Now imagine that I am a giant monster, and that distance is not 3 meters, but it's 300,000 kilometers. All right? So if I try, I will try again, okay, to go back there. So if I do it again, 1, 2, 3. Now I'm traveling at what speed? 100,000 kilometers per second. And nature doesn't like that. She's starting to get nervous. Oh, Pablo, what are you doing? Okay, you're approaching 300,000 kilometers per second, which is speed of light. So you're approaching it, and nature doesn't want that. She doesn't like it. So what's nature gonna do? Nature's gonna stretch that distance, make it shorter. It's gonna make my watch tick a bit slower, and if I dare to actually speed up, it will make me feel heavier. So that it's more and more complicated to actually speed up and reach that velocity. Of course, this is a really, really simplistic way to explain spatial relativity. I hope you don't feel insulted by this, but that's what nature does, okay? So nature, if it's convenient, just to make sure that the laws are obeyed, nature will change space and time in a particular way. So that's the takeaway message. And now, another experiment. We're going to test general relativity. And for that, I'm going to use, again, the car. So we haven't tested it before. I hope it works. So what I'm going to do is I'm going to push this car, and you're going to see it right there. I hope you can see it. Did you see it? It went from right to left because I pushed it. Now, let's use the principles of general relativity, and I hope Walt is fine with that. We're going to test that again. What do you see? You saw the same thing, right? This is a very stupid way to prove that it is not possible, in principle, to distinguish the effects of gravity and the effects of some acceleration. And that is very important, and it has a lot of consequences. So if we put together the two ingredients that I mentioned, right, that nature sometimes bends space and time in a particular way just to make sure that relativity is always working, and given the fact that we cannot distinguish the effects of gravity from the effects of some acceleration, we can say gravity and curvature in space and time are the same thing. That is what general relativity is all about. And if we have some big objects like black holes that are curving space-time dramatically, and they merge with other black holes and do a lot of catastrophic things, then space-time is going to feel perturbed. And those perturbations are going to move away in space and time. So what is a perturbation of space-time? What is a perturbation of the gravitational field? Gravitational waves. As I said before, electromagnetic waves are perturbations of the electromagnetic field. Gravity waves are the same thing, but for gravity. So now, I'm going to show you how gravitational waves look like. And for that, I need a volunteer. Not going to get hurt. Who wants to come here to the stage and feel gravity? We have some volunteer there. You want to come up here or down here? Hey, what's your name? Spencer. Hi, I'm Pablo. Nice to meet you. Do you want to come here? We're going to show everybody what a gravitational wave passing by will do to your body. I hope it doesn't hurt much. Okay, are you ready? Okay. This is what a gravitational wave is doing to Spencer. A gravitational wave is stretching space in a particular direction and then stretching it in the perpendicular direction. But this gravitational wave is huge, right? So you may be wondering, if we can see, if gravitational waves are this big, then we don't need a telescope or observatories or anything. We can just see how Spencer is actually moving around, and we just know that there is a gravitational wave. Okay? Thank you. Thank you very much. You can come back. That's all I wanted to prove. The problem is that the gravitational waves that we are trying to detect are small. This amplitude, if that is a true gravitational wave, the amplitude is about 1. That means that the deformation that they produce in the screen is about the same size of the screen. Okay? So if a gravitational wave was, for example, a tenth, like 1/10, then the deformation in the screen, the deformation in Spencer that it will produce, it will be just 1/10 of the size of Spencer. All right? If it was a gravitational wave with an amplitude of 1/100, so then Spencer will be stretched and squashed by just 100th of a Spencer. That's not a international units measurement, but okay. So the gravitational waves that we are trying to measure have an amplitude of 10 to the minus 21, typical gravitational waves. And you probably don't have a sense of what the number is because it's just too small. Well, 10 to the minus 21 means 1 divided by 100,000 billion trillion. I don't even know the word for that. What is it? I don't know. It's like this number: 1 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0. Another one: 0 0 0 0 0 0. That's the number. So you have to divide Spencer in that number of little parts, and if a gravitational wave passes through him, that little part, that will be the size of the deformation that Spencer will feel. It's small, right? It's small, but it has been detected. So we know now more or less what they are, but we don't know how we can measure such tiny things. And it's, of course, challenging, as you can imagine, because they're very small, and there are different ways to do it. I'm going to explain 2 of these ways to detect gravitational waves. One of them is called pulsar timing. So what is a pulsar? A pulsar is a neutron star, a very compact object that they emit a beam of light on the poles, and they're spinning. If that beam hits Earth, we can see the flashes of this pulsar. So if you have some observatory, you will see that every time that that neutron star is rotating and the beam hits Earth, we will see a pulse in our data. Good thing is that these pulsars are very, very, very precise. They are extremely heavy. They are more or less the mass of the sun, but very small. So their radius is typically like 10 kilometers or so. So it's like the distance between here and Brunswick, for example. So we see these pulses every few milliseconds. That means that whole thing is spinning with a period of about a few milliseconds. If we have several pulsars in the sky, which we have, and we're observing them for a long time, blip, 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 everywhere in the galaxy, and gravitational waves passes on the way, these pulses are not going to arrive exactly when they were expected, but they're going to be maybe a little bit earlier or a little bit later because space is being deformed, right? So that's how we are trying to measure gravitational waves, in particular from supermassive black hole binaries. That's what is called the pulsar timing array. By the way, who can recognize this observatory here? So I suppose everybody has seen the movie The Dish. That's the one. That's Parkes. But now I'm going to talk about another experiment, which is LIGO. It's the Laser Interferometer Gravitational Wave Observatory. This is the detector that has detected the 10 to the minus 21 thingy. Yeah, these guys here, Paul and Letizia, they are the ones that have detected gravitational waves, among other people. So I'm going to explain how LIGO works. This is a 4-kilometer arm, 4 kilometers going this way, 4 kilometers going this way. Those arms are empty. And there is a laser coming from here all the way to the end of the arm. It bounces there. There is a mirror at the end of the arm, and then the laser comes back to the same place. At the same time, when you shoot this laser, you shoot another one going this way, and it goes here. It's not in the picture, but there's another mirror here, and then it bounces back all the way, and after 4 kilometers, both beams will find each other again, and the arms are going to be moving in a particular way if a gravitational wave passes through it. So then you can measure a little interference, right? The two lasers will not arrive at the same time because they have been traveling different distances. One of them is a bit longer than the other. These arms are now the Spencer, okay? So now instead of Spencer, we have this 4-kilometer arm. The arm length of that detector was increased by 10 to the minus 18 meters, which is, again, a small number. Divide a meter by 1,000,000 little parts, take one of them divided by 1,000,000 parts, take one of them divided by 1,000,000 parts, and that's how much the arms of LIGO stretched. And that's how they detected gravitational waves. They measured the masses of the black holes. It was a 36 solar mass black hole and a 29 solar mass black hole. Okay? They merged together in the way that I showed before, and they combined and they became one black hole of 62 solar masses. It should be 65 solar masses, the sum of the two masses, but it's actually 62. The rest of the mass has been spread. That's what has been emitted in gravitational waves. And that's the story of the merger. That's the story of Alice and Bob. That's why we can see them, because they have emitted a tremendous amount of energy. In fact, when they were merging towards each other, they were so luminous, they were so bright in gravitational waves, that they were emitting more power than the rest of the universe. If you put the sun and all other stars in the galaxies together, and you take all other galaxies in the universe, you put them together, and you measure how much energy they are emitting in a second, Alice and Bob were brighter than that. So we have a pair of black holes, like 30 solar mass each, and they're spiraling around for a long time, and then at some point they're emitting really strong gravitational waves. They become the brightest objects in the universe. They are brighter than the rest of the universe put together, and then at some point they emerge, and they produce really strong gravitational waves. When that happened, there were not even humans on Earth. There were not even dinosaurs. It was like 1 billion years ago. And those waves have been traveling through space for 1 billion years. They have been traveling through the entire space. And in September 14, they arrived at the detector. They produced a little stretch in the arm length of smaller than the size of a proton. And these people detect this signal. And everybody's excited because the first detection of gravitational waves, somebody is going to win the Nobel Prize. And all this excitement because of this blip. That is the story of Alice and Bob. This is the blip. This is what has been detected. That's the merger of two black holes. This is the first heartbeat of gravitational wave astronomy. Thank you very much.